Good morning students. Welcome to your beautiful channel that is 33.physics for you. Now in this video lecture we are going to solve examples of chapter 1 based on flux, electric flux, right? So basically these 2-3 video lectures will be based on examples related to flux. So before starting examples related to flux, let us discuss what is flux. So you must be knowing that flux phi is defined as integration of E dot dA for a small element A. For a small element having area dA, flux will be integration E dot dA. If total area is A, then flux will be vector E dot vector A, or if you want you can write this as EA cos theta, right? So flux phi is EA cos theta. Also, according to Gauss theorem, we know that flux phi is net charge sigma q over epsilon naught. You can write net flux is total charge enclosed by closed surface to epsilon naught. Here sigma q is the total charges which are enclosed by closed surface, right? Suppose if we have a closed surface like this, and here we have charge q1, q4 and q5, let us say q2 and q3 are outside the closed surface, then this sigma q will be q1 plus q4 plus q5, right? And in this equation this electric field will be due to all the charges, right? So if you write equation like flux phi is equal to integration E dot dA, which is equal to sigma q over epsilon naught, then in this equation this electric field is due to all the charges, while this sigma q is only enclosed charges, that is the charges which are enclosed by closed surface. Clear? So let us start with example, or let us say exercise 1.15, a quite simple example, exercise 1.15. Consider a uniform electric field E vector which is given as 3 into 10 to the power 3 I cap. Electric field E vector is given as 3 into 10 to the power 3 I cap Newton per coulomb. A. What is the flux of this field through a square of 10 centimeter on side whose plane is parallel to YZ plane? We want to find flux through a square of length 10 centimeter, side 10 centimeter. That is, you can write 0.1 meter on a side whose plane is parallel to YZ plane. Here you can see that electric field is along x-axis. E vector is along I cap, that is along x-axis, and this square is along YZ plane. So if we draw XYZ axis, let us say this is x-axis, this is y, and this is z-axis. We have XYZ axis, right? Then electric field is along x-axis. This is the direction of electric field, right? And the plane is kept along YZ, right? So if we consider a rectangular plane, sorry, a square, it is kept along YZ plane. So this is the square which is kept along YZ plane. Now here you should know that area is a vector quantity and that area is always perpendicular to the surface. So if we consider this square, then its area will be perpendicular to its surface. So this will be the direction of area vector, right? This is the direction of electric field and this is the direction of area vector. So clearly you can see that electric field and area both are in same direction. You have to always remember that area is a vector quantity and its direction is always perpendicular to the surface, right? So here for this surface, area is perpendicular to that surface. So plane is kept along YZ, right? So area will be along x-axis. So electric field and area both are in same direction. So here we know that the flux associated with the square will be, the flux associated with the square will be, with this square will be flux phi is equal to vector E dot vector A, right? So in two different ways you can solve. So flux phi is equal to E is 3 into 10 to the power 3. Now what is area of a square? We know that area of a square is L square. So that is 0.1 square is 0.01 meters square. And this area is along x-axis. So you can write 3 into 10 to the power 3 I cap dot 0.01 I cap. So 3 into 0.01 is 0.03 into 10 to the power 3 I cap dot I cap. Let us write one more step, I cap dot I cap. So I dot I will be 1. So this will be equal to 0.03 into 10 to the power 3. So that is 30. Flux is, electric field is Newton per Coulomb and area is meter square. So Newton meter square upon Coulomb will be its unit. There is one more way to solve the same example, that is the flux associated with this is given by E dot A. Let me write directly, phi is equal to vector E dot vector A, which is equal to EA cos theta, right? So that will be equal to, E is given as 3 into 10 to the power 3, area is 0.01 and angle between these two is 0 degree. You can see that both are in same direction, right? Both are along x-axis, so angle will be 0. Cos 0 is 1. So again 3 into 0.01 will be 0.03 into 10 to the power 3 is 30 Newton meter square over Coulomb. Right? This will be the answer. This is actually part A. There is one more part, part B. What is the flux through the same square if the normal to its plane makes a 60-degree angle with the x-axis? So in second case, it is given that this plane is making angle 60 degree with the x-axis. So if we draw the plane, let us say this is xy z axis, let us say this is y, this is x and this is z axis. We have xy z axis. Now plane is kept in such a way that it is making angle 60 degree with x-axis. So its area, actually area vector A is making angle 60 degree with x-axis. So we can say that the plane is kept something like this, right? So area will be perpendicular to it and this area is making angle 60 degree with the x-axis and electric field is along x-axis. Obviously this is the direction of electric field, right? So angle between electric field and area is 60 degree. So in that case, for case B, here let us write here, for case B, flux phi is equal to EA cos theta, which is equal to E is 3 into 10 to the power 3, area is 0.01 into cos 60. So 3 into 10 to the power 3 into 0.01 into cos 60 is half, right? So this is obviously 30 as we have calculated. 30 divided by 2 is 15. So answer will be 15 Newton meter square over Coulomb. Clear? 15 Newton meter square over Coulomb. Quite simple, just you have to remember this formula. Okay.